In the last video, we talked about applying a magnetic field in order to align the nuclear spin that goes on in a molecule. Now, did you see what I just did? I gave you a very sciencey sounding statement. And if you watched the last video, you probably followed that statement pretty well. Okay, we've got the nuclei, they're in a spin, it's a constant spin. We apply a magnetic field in order to align all of the spins up in the same order, and now we go on to step number 2. And in the last video, we said step number 2 is this concept of move. We have to get things moving. All right, so the way that we do this, attention, everybody, up in order, all facing the same direction, get ready to march. Well, now what we do is while they're all standing upright, facing in the same direction, we apply a second or another magnetic field. Kind of like 2 here, right? One gets them to align, and the second one we're going to play around with. So again, I want you to go back and think about the poor little lazy kid that's on the swing. That's not a very good swing. I'm not a very good drawer. And he's just sitting there. That's kind of what's happening right now. The nuclei are sitting there. Nothing's going on. Perfectly happy with what they're doing. They don't have to move on the swing. They're A-okay. And the second magnet's going to come in, which will be kind of like you. And maybe you go behind this little lazy kid, and maybe you decide to give it a little nudge. A little push. That's our second magnet. We give it a little push, and the swing swings back. And we push again, and the swing swings back. And push and back. And push and back. And push and back. And push and back. Notice what I'm doing. On the swing set, what's going to happen? The more times that you push, well, there's a chance that that swing is going to go higher and higher and higher. So this motion of going forward and coming backward and going forward and coming backward and going forward and coming backward, this is what we call resonance, folks. So now we have the M, magnetic, and now we have the R, which is resonance. It's this back and forth motion that's going to happen with these nuclei when we apply this second magnetic field onto it. Now, that first original magnet, this very first one that we have put in place, this one's pretty strong. It has to be strong. They all have to line up in the same direction, do the same thing at the same time. It's got to be a strong magnetic field that we apply there. The second magnetic field that we come in, this will be your pushing stage. And these will be very teeny tiny little bitty pushes that begin to push those nuclei and kind of swing them back and forth. Think of this like a top. You know, if you ever played with a top, and probably most of you haven't, well, you spin the top on the floor, and in the beginning, it's spinning, 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 and then as it slows down, it begins to tilt over to the side, right? That's kind of what we're doing here. We are pushing these nuclei, and the nuclei will maybe have an initial spin like this. The traditional kind of how we represent it left to right. Over time, however, as we put in that second magnet, that spin could kind of go lopsided, and that spin could kind of go lopsided again. And we could start to see these changes in the spin state. So the regular back and forth motion that happens on the swing set, that is called a resonance. And nuclei do the same thing. You have to give them pushes. And as you push them, they kind of go back to their start state if we don't continue to push and push and push and push. Their spins begin to change. As we push more, the swing goes up higher. As the swing goes up higher, we can get these little kids to scream. Maybe we push them so much that the swing goes upside down. I hope so. I hope those little kids scream as they go upside down on that swing. I would like to see that. So now, again, we're talking about kindergarten terms, but we're applying it to nuclear magnetic resonance. The same happened to nuclei, folks. There's no difference. You put resonance or a magnetic field onto these aligned nuclei that are in compounds and molecules. And over time, as you push maybe more and more energy into the system, you can get these nuclei to begin to change and tilt their spin. And when the small pushes turn the spin on its side, or in the swing set, upside down, well, they begin to spin differently. To get this to flip like this, to get this to spin differently than how it was in the beginning, we call this the precession speed. The precession speed is much slower than what we call the normal aligned in the very beginning state. And that kind of makes sense. This is in the unnatural position. And in that unnatural position, they're not going to want to stay in that for a very long period of time, right? So it will continue to spin, but the precession speed slows down versus the normal spin that they have in the very beginning. Now, this precession speed, it relies on a couple of things. And number one are the nuclei properties. And as you can imagine, the nuclei of hydrogen is different than the nuclei of carbon, which is different than the nuclei of nitrogen, which is different than the nuclei of phosphorus, or any of the other ones that we want to talk about. All the nuclei are going to be different. They all have a different number of protons, they have a different number of neutrons, and so forth. So the precession speed is somewhat like a constant, and that constant is going to be determined by, number one, the nucleus itself. They're all different, so therefore precession speeds are going to be different slightly as well between atom to atom to atom. Next are the rate of the spins. Different nuclei spin at different rates. So precession speeds, of course, are going to be a little bit differently depending on what atom that you're focused on and what atom that you're doing. And number three, you're also going to see a direct relationship to the magnetic field. This also has a role in the precession speed. But all that we need to know is that precession speed is a constant, and it should stay constant for all of the atoms in the molecule of the same type. So, hydrogen NMR, all hydrogens will behave similarly, and they all have a similar precession speed because they're all hydrogen nuclei. Carbon's different. Therefore, we tweak the machine in order to just look at carbon. That's how that's done. Nitrogen's different. We tweak the machine because that takes some extra pushes in order for these atoms to give us that type of signal. So we can follow this up, precession speed, with a term called precession frequency. And precession frequency is basically the strength that it takes in order to tip, and I'm going to put that in quotes, the nuclei away from the main magnetic field. In other words, we're kind of looking at how large the kid is that's on the swing. Right? Atoms are the same way. Some atoms are much bigger and larger than others, and some children are much bigger and larger than others. So if they're sitting on the swing set and we have to go in and push them from behind, well, some of these atoms won't require a lot of effort at all because they're super tiny and super small, and it doesn't take a lot of effort to get the swing to flip or to change their spin. Other atoms, though, like kids, are much larger, and it's going to take more oomph to get them to start pushing and to get their spins to flip. So precession frequency is that concept. It is the strength that it takes to get that kid to flip on the swing set. Now, here's the good news. Like everything, what goes in has to come out. So once you get that kid to flip, or the nuclei to flip its spin, let's say that you stop pushing them. You don't push them anymore. What's going to happen? Well, that screaming little kid will eventually come back down to ground state. Back into the spot that he or she started in. So if I stop putting energy into the system, this swing is going to continue to swing. But over time, it loses momentum, right? So it doesn't swing as high forward or backward, and the next time it's a little bit lower and lower and lower, and then sooner or later it will come back to a stop. That swing will come to a stop just like it was before we started pushing it. We can push it for a couple of seconds and then stop, and then it will come back down to the natural spin state, and it will align with the magnet yet again. Nuclei behave in the same way, folks. There's no difference here either. These pushes, if those pushes of energy stop, then the atomic nuclei will eventually align back up with the magnet, and they will eventually spin like they were in the very beginning before you began pushing them with this energy in order to try to get them to turn. Quick burst. That's all we need. And then they will flip back over after they scream a little bit, and they will come back down to a rest position. What energy is needed in order to do the pushes with? You might be surprised. The only thing that's needed here are radio waves. That's right. If you listen to a radio anymore, nowadays, what is it? On your phone, on your laptop, Pandora, Spotify, whatever the crap is that's out there now. Well, if you listen to a radio in your car still, you're getting radio waves. That's how you're listening to people's voices, through your instrumentation that's in your car. And it is not uncommon to see NMR using radio waves to do the pushes with in order to get these molecules to flip. And some of these NMR instruments, they use the exact same frequency as your FM radio. And they typically go 88 to 180 megahertz. Think of that the next time that you turn on your radio. 107.5 is typically a popular radio station here. Well, 107.5, that kind of fits in that range, doesn't it? That's a radio wave. You're listening to a person's voice through an instrument that could be screaming at you, that they call a song, all due to a radio wave. And the radio wave is the exact same radio wave that gets these molecules to start swinging, to start pushing, to start trying to get them to flip their spin state. So I keep kind of referring to this state where the swing at some point in time with the little kid on it will go all upside down and scream. He wants off. Think of those awful amusement park rides. You know, you pay $5-10 to get on a ride that's probably rusted and getting ready to fall apart, and then they put you on it and the ride gets stuck and you're stuck upside down. What are you going to do? You're going to start screaming. These kids are going to start screaming. The nuclei are going to start screaming because they're out of alignment. They are out of alignment with the radio waves that are coming in to force them to flip. So to blow your mind even more, these little nuclei, the nucleus that's in each side of these atoms, I want you to think of them, because they do spin and they do flip and they do come back down. They're like a little tiny radio station. Right? Each NMR is equipped with a radio receiver to catch the screams that come from these kids or come from the nuclei. They're broadcasting a signal. We're putting radio waves in. We're going to kind of get radio waves out. That machine is going to pick up those radio waves, and it's going to tell us, hey, this nuclei is doing this at this step or this stage of the process. Now, I told you the swing will eventually come back down. And you're probably thinking, well, wait a minute, this is nuclei. What makes them kind of go back down to ground state? Well, if you are on a swing set, what's going to happen? It's probably going to be due to friction. The little kid is probably going to drag his or her feet. That slows the swing down so it can come to a stop a little bit more. Nuclei are the same way. Nuclei swing will slow down, and they don't have feet, but here's the thing. The sample is typically in some type of solvent, and that solvent is the ground. And the sample, which is what you're trying to measure, that's the kid. So when these things begin to flip and when they begin to broadcast a signal and scream and we stop movement on them and they come back down to ground state and ground spin, then something's going to have to slow them down. What slows the swing set down and makes it come to a stop? It's because the sample molecules drag their feet against the solvent molecules. This whole process is called relaxation. So if you are in the NMR world and someone uses the term relaxation, that is what they're referring to. It is this flip that's beginning to come back down to the start position, and over time it slows and it slows and it slowed. Now, these are just some of the basics, folks, that happens with NMR. And again, it's not very scientific-y. That's not the way that I work. I want to put things in perspective that you can relate to so that this doesn't become a hodgepodge of chemistry and physics, because nothing's more boring than physics. And then you mix in chemistry on top of that. Give me a break. So we're not yet done, though. We're not yet done with the story of NMR. There's kind of more to it. And there's more details that we need to talk about before we can fully start understanding what goes on in the interpretation of an NMR spectra. And that more to it is to come in the next video. So if you've got the time, don't walk away from your computer. Come back, take a seat, pull up a chair, get a snack, and we'll come back and we'll talk about more details of NMR.